Hello everyone. Today we will see what is convolutional neural network. Convolutional neural network, it is a deep learning algorithm which can take input image, assign importance, that is the learnable weights and the biases to various aspects or objects in the image in order to differentiate them from one another. And the pre-processing which is required in CNN, it is much lower as compared to the other classification algorithms. So in primitive methods, the filters are hand engineered with enough training, whereas in CNN, these have the ability to learn these filters, and the CNN are composed of multiple layers of artificial neurons. It is analogous to that of connectivity pattern of neurons in the human brain, and the CNN, it is composed of many layers of artificial neurons. So here the first layer, it extracts the basic features such as horizontal or the diagonal edges, and the next layer, that is this output of the first layer, it is passed on to the next layer which detects more complex features such as corners or the combinational edges. And as we move deeper into the network, it can identify even more complex features such as objects, spaces, etc. So these are the four layers of the convolutional neural network. Here you have first is the convolutional layer, then you have the ReLU layer, that is the rectified linear unit layer, then you have pooling layer, and last is the fully connected layer. We will see all the layers one by one. First is the convolutional layer. Here this layer, like why we use a convolution layer, because before the concept of the convolution was presented for the digit classification, people used other methods like SVM, that is the support vector machine, then KNN, K nearest neighbor, logistic regression, etc. in order to classify the images. In those algorithms, pixel values were considered as features. That is, for a 28 cross 28 image, there would be 784 features. Now, these multiple convolution filters or the kernels will run over the image and compute a dot product. So each filter extracts different features from the image, and after performing the convolution, we get the convolved feature which is called as the feature map. So here we will consider an image of size 5 cross 5. That is, there are 5 rows in this and there are 5 columns. And we will consider a filter or kernel of size 3 cross 3. Okay. And here we perform element-wise multiplication between the image pixels values that match the size of the kernel and the kernel itself and sum them up. And this provides us a single value for the feature cell. Okay, like this. That is, here we will multiply like 2 into 1, then 4 into 2, okay, plus 9 into 3, then you have 2 into minus 4, plus 1 into 7, plus 4 into 4, plus 1 into 2, plus 1 into minus 5, and plus 2 into 1. So when you multiply these, you will get 51. Similarly, what we do is we will move the filter, okay, and that is, we'll continue to run the filter on the image and will produce the new values which are shown here. Okay. Now here you have to move this filter one after the other. First we have kept on this, that is 249, 214, 112. Then next we have to keep it on this value, and that is this part of the image, that is 491, 144, 129. Then we'll get 66. Similarly, we'll move this. So here we'll get, the next will be 914, 446, 292. Okay. So again, you have to multiply these values, these 3 cross 3 values with this filter. So you'll get 20. Okay. So here is one more example for this, that is 4 into 1 plus 9 into 2 plus 1 into 3. Similarly, plus 1 into minus 4 plus 4 into 7 plus you have 6 into 4. Sorry, here 4 into 4. Then you have 1 into 2, 2 into minus 5 plus 9 into 1. So when you multiply and all these, you will get 66. Okay. Similarly, you have to do it for all the parts of the image here. Now here just a minute. So here what we are doing in this example, we are sliding the kernel by one pixel, by 1 pixel, and this is called as stride. So we can have the kernel move by different strides. That is, you can move it by 1 pixel, by 2 pixel, by 3 pixels in order to extract different kind of features. And the amount of stride we choose, it affects the size of the extracted feature. Okay. So here we are getting the feature vector as the size as 3 cross 3. So when you make the stride value as more, you may reduce the size of the feature. Now, this is the formula to calculate the feature size. So, feature size is equal to image size minus the kernel size divided by the stride plus 1. So, here in this example, what we have taken the image size as 5 cross 5. So, it is 5. Kernel size is 3 cross 3, and we are moving it by 1 pixel. So, that is nothing but 1 stride. Okay, stride value is 1 and plus 1. 5 minus 3 is 2. 2 divided by 1 is 2. Plus 1, that is 3. So we got the feature vector of size 3 cross 3. So with a stride of 2, the kernel size of 3 cross 3 on an image of size 5 on 5 into 5 would only be able to extract the feature size of 2. Okay, if we change the value of this stride as 2, that is here it is 2 sorry, here stride value as 2. Okay, then 2 divided by 2 will be 1, 1 plus 1 will be 2. So here the feature size will be reduced when you increase the value of the stride. Okay, so here again we are taking one image which is of size 5 cross 5, and we are multiplying it with a filter with size 3 cross 3, and we are getting this value, and this is for, that is, we are taking the stride value as 2. So here the feature value feature size is changed. In the previous slide, the feature size was 3 cross 3 because the stride value we have taken it as 1. But here in this example, we are taking the stride value as 2, because of which the feature size or the size of the feature, it has been reduced by 1. Therefore, now the size of the feature is 2 cross 2. The next step is padding. So here what if you want the feature to be of the same size as the input image? Okay, we don't want to reduce the size of the feature. What happened in the previous step, the size of the feature was reduced. Okay, it was not as that of same as that of your input image. But what we should do if we want to keep our feature size to be same as that of the size of the input image? Okay, so this can be achieved by a technique called as padding. Okay, so here it is a technique to simply add zeros around the margin of the image in order to increase its dimension. So here by doing this padding, it allows us to emphasize the border pixels, and here we will lose less information. So for example, suppose we were having our 5 cross 5 image. So what we are doing here, we are adding the, or we are padding this image with what? With zeros here. Okay, that is here across all the 4 sides we are adding here. Now again we will take the filter. The filter will be of size 3 cross 3. We will multiply this and we get the feature of this size. That is, the feature of this will be now as that of the feature of the image size. So here our image was 5 cross 5 and our feature is also of the size 5 cross 5. Okay, so here what we are doing now, this is the formula which is used for padding. So feature size will be what? Image size plus 2 into padding size. Okay, minus the kernel size. Kernel size is 3 cross 3 divided by the stride plus 1. Now here, what is the padding size here? The padding size is 1. That is, we are adding one row and a column across all the 4 sides of the image. Okay, so here the feature size is equal to image size is 5 plus 2 into padding size is what? 1. Okay, 1. Then minus 3. Kernel size is 3. 3 cross 3. 3 rows, 3 columns. Then divided by the stride. So here we are considering the stride to be 1 plus 1. So we'll get 5. So the size of the feature is nothing but 5. Okay. So this is nothing but the padding. So here, what after padding, the size of the image, it has become 7 cross 7. Fine. Now, next is the ReLU layer, that is the ReLU activation function. It is nothing but the rectified linear unit. So here convolution operation, it is a linear operation, that is dot product is applied and we are applying the summation. Now we want to provide non-linearity. Okay, we want to provide the non-linearity as convolution is linear operation. So to provide the non-linearity, what we are doing, we have to apply the ReLU activation function. Fine. Now activation function, these introduce non-linearity to the model, which will allows it to learn complex functional mapping between the input and response variables. So different activation functions here are ReLU, you have sigmoid, you have tanh, then you have leaky ReLU, and you have many more activation function which can be used to convert the linear operation to the non-linear operation. Now, after every convolution operation, ReLU activates the ReLU activation function will be used, and the ReLU function, it is a piecewise linear function. That is, it will output the input directly if it is positive. That is, if it is greater than 0, we'll get the same output. If it is less than 0, that is, if it is negative, then the output will be 0. Okay, if the value is positive, we'll get the same value. If the value is negative, we won't get any value for that. Simply we'll get a 0. So here the ReLU of x is equal to max of 0 comma x. Now in ReLU, whatever input you give, you get the same output. But if the value is negative, the output will be 0. So there is no negative value in the ReLU. All values are positive. So ReLU, it is most used in it is mostly used in the activation function because it is easier to train and it often achieves better performance. So ReLU, it can be used before or after the max pooling layer. Therefore, it satisfies the commutative property. That is, you can use max pooling after the before the ReLU, or you can use the ReLU before the max pooling. Okay, so in general, ReLU is applied right after the convolution layer, and then that output is max pooled. So it satisfies what? It satisfies the commutative property. And in practice, it is applied what? It is applied after the convolution layer, and then that output is max pooled. So the advantage of using the ReLU is it does not activate all the neurons at the same time, and it allows the models to learn faster and perform better. And it overcomes the vanishing gradient problem also. So we should use why we should use the activation function, because it decides whether a neuron should be activated or not by calculating the weighted sum and then further adding bias to it. Okay, then next we have so this is nothing but the ReLU layer, that is it will be having either zero value or the maximum value, okay, or the positive values. And here it introduces non-linearity to the network, and the output is what? It is a rectified feature map, and it will perform element wise operation, and it will set all the negative pixel values to zeros. Now next we have pooling. So pooling, it reduces the dimensionality of the feature map, and it combines a set of values into the smaller number of values. So it provides the valuable information by keeping the useful information and eliminating the irrelevant information. Okay, so it will keep the useful information and it will eliminate the irrelevant information. So here it will reduce the it will reduce the computational complexity of the upper layers by eliminating some connections between the convolution layer. Okay, and it will execute the downsampling on the feature maps coming from the previous layer, and it will produces new feature map with a condensed resolution. Fine. So the two main purposes of pooling are to reduce the number of the parameters or the weights, and thus lessening the computational costs, and second is to control the overfitting. So these two are the main purposes of the pooling layer. Now you have max pooling, average pooling, and mean pooling. We'll see what is max pooling. So max pooling, it helps to reduce the spatial size of the convolved features, and it will help to reduce the overfitting by providing an abstracted representation of them. And it is similar to convolution layer, but instead of taking a dot product between the input and the kernel, it will take the sorry, it will take the maximum of the region from the input overlapped by the kernel. Okay, so here we'll see it by an example here. So here you have a max pool layer operation with a kernel of size 2 cross 2 and the stride of 2. Okay, so here stride of 2 we are taking and the kernel size is 2, so it will first it will take 1 4 2 6, so 1 4 2 6. So here the what is the maximum value in all this? It is 6, so we are getting 6 here. Okay, then next 2785. Next the filter will come here because we are taking two strides, so it will give now these two columns and it will come to this part of the image. So 2785, maximum is 8. Then you have 3412, out of this maximum is 4. Then 0731, so here maximum is 7. Okay, so this is how the max pooling is been done. Next you have the average pooling. So in average pooling, here we take the average value instead of the maximum value. So this is the figure for that. So again here we are taking the kernel size as 2 cross 2 and the stride is 2. So here average of 1426 is 3.2. Similarly 2785 average is 6.2. Then 3412, its average is 2.5, and the last one is 2.7. So advantage of using the max pooling, it is nothing but it reduces the noise by discarding the noisy activations, and it is better than the average pooling. Okay, so next we have the flattening. So this flattening, it will convert all the 2D resultant two-dimensional arrays from the pooled feature maps into a single long continuous linear vector. So this is how it has been done. So here you will take the pooled feature map. So previously what this is the max pooled feature map, that is 6847. So here it has been flattened. Here we'll get this in this form, that is 6847. So we'll get the flattened feature map as like this. So next we have the fully connected layer. Now in the fully connected layer, the input layer nodes are connected to every node in the second layer, and there will be one or more fully connected layers at the end. And adding a fully connected layer, it will help to learn non-linear combinations of the high level features outputted by the convolutional layers. So here when the data the data is passed in one way from the input to the output layer, the fully connected layer, it is composed of four layers. Input layer, then you have hidden layers, that is the first and the second, and the output layer. So the input layer, it receives the features of the network, that is the flattened matrix which we have obtained in the previous step. And the first hidden layer, it contains the weighted inputs from the input layer, and it will send the data from the previous layer to the next layer. And here one of the additional layer, it makes the fully connected layer capable of solving the non-linear classification problems. The output layer, okay, the output layer, it consists of the classification result, and there are several algorithms which are used for learning the step of fully connected layer. The supervised learning technique, it is called as the back propagation, and it consists of four stages, that is the initializing the weights, then you have feed forward, back propagation of errors, and the updating the weight, that is weight update. Now this is the entire process of the CNN. So what we are doing here, we are taking some pixels from the image, and these are fed to the convolution layer, which will perform the convolution operation, and it will result into a convolved map. Then the convolved map, we are applying ReLU function to generate the rectified feature map. Okay. Then image is processed with multiple convolutions here, and the ReLU layers for locating the features. Then different pooling layers with various filters are used to identify the specific part of the image, and the pooled feature map, it is flattened, and then it is fed to the fully connected layer in order to get the final output. Okay, this is about the convolutional neural network. So here I have covered some important parts. If you want detailed explanation, I will try to do it in the next video. Hope you have understood. Thank you.